You may remember that I have said on occasion in class that most of the spring semester of organic chemistry is all about carbonyl chemistry. Well, you're about to see that in droves as we continue the same kinds of chemistry we saw in Chapter 17, but now with weak nucleophiles instead of not so weak nucleophiles. So let's get started. A quick comparison. Chapter 7 focused in on the addition of really hard nucleophiles, Grignards and hydride reducing agents, to the carbonyl CO double bond, and that invariably gave you direct addition right at that carbon. What we're going to see in Chapter 18 is the addition of soft nucleophiles that also add directly when there's only one choice. They add directly to the CO, but the outcome is a little bit different. The first step in the mechanism is still the same. The outcome is slightly different depending upon the nucleophile. We're also going to have a wonderful opportunity in Chapter 18 to review acid-base chemistry. So it's really not a bad idea to review that chapter from 2301. There'll be a lot of emphasis on oxygen nucleophiles, and then there's two reactions thrown in that are kind of oddballs. Reductive amination and the Wolff-Kishner. You know, they fit in here tangentially. The main focus of Chapter 18, though, is a reaction called the aldol. So that's what lies ahead. Let's just get started with an introduction overview. As I've already mentioned, the CO double bond is still the electrophile all chapter long. But our new nucleophiles are nucleophiles that have heteroatoms, like oxygen, nitrogen, sulfur, phosphorus, and we will see that the cyanide anion is a good weak nucleophile for adding to the CO double bond. A really big player, and we know this is a weak nucleophile and a soft nucleophile, is the enolate anion. And just a quick reminder that the enolate anion is that anion that results from deprotonation at the alpha carbon. Now, as I mentioned in the outline, there's these other reactions that get kind of thrown in, but they're good foreshadowing for what's to come. So, you may become overwhelmed. It will definitely seem like a lot, but you're going to get tired of hearing me say this, I'm sure. But basically, if you think mechanism, you will be able to continue to breathe. And that's really a goal. Alright, so back to acid-base chemistry, and acid-base specifically, catalysis. All of this chemistry now, you're going to want to think about the mechanism and what is the first step. It depends upon what you're using and what the conditions are. So if you think about Chapter 17 chemistry, all of these reagents are super basic. Ooh, definitely not that one. We got H minuses, that's a strong base. C minuses, super strong base. So point with that is there was no way you could have any source of acid around, or else, well, pretty much it'd be sayonara to your nucleophile. They'd all get protonated and you'd have nothing. You'd be dead in the water. So, Chapter 17, no acid catalysis was even an option. But now, when we're using these weak nucleophiles, we can have acid catalysis, or for that matter, basic catalysis. So, going back to our mantra of acid base always wins, because it's a really fast reaction, this means if you have an acid catalyzed reaction in this realm of chemistry, the first step will invariably be protonation of your carbonyl. Okay, so I'm going to put a box around this. If your reaction is acid catalyzed, this is what's going to result. That will be the first elementary step. All right, well, so what? Why is this important? Well, it's important because you can get the reaction to go more efficiently, more quickly, and ultimately you'll have a better outcome. So by protonating that carbonyl, you're really boosting the electrophilicity of your carbonyl carbon. So I've got a delta positive there that is really, really accentuated by the fact that you have a full-fledged positive charge on that oxygen. In fact, what you want to think about is how you can draw a very good resonance contributor right here that shows, woo-wee, that positive charge can be put on that carbon. That definitely makes the subsequent addition of a nucleophile much faster. And I don't know why I showed that second arrow. That's crazy. That's all I need to show right here. This oxygen adding to that carbocation to give you this charged intermediate. So my electrophile, the carbon of the carbonyl, is made a lot more electrophilic just by protonation of the carbonyl. Okay, so do we always use acid catalysis? Well, no, because you have to admit that neutral nucleophile is pretty weak. So under basic conditions, I actually have a much stronger nucleophile. So the bottom line here is that in the chemistry that we'll see in this chapter, we're going to do one or the other. We're either going to catalyze the reaction to go more quickly under acidic conditions by making our electrophile more electrophilic, or we're going to catalyze our reaction under basic conditions by using a catalytic amount of this base, and in so doing, that makes the reaction go a lot more quickly because my base is stronger. Those two principles are key in this kind of chemistry. So the take-home message, you've got to think about the conditions, think about your reagents and what is present in the beaker, if you will. Do I have acids floating around, or do I have bases floating around? Do I have positive charges floating around? Acid conditions. Or do I have negative charges floating around? Basic conditions. All of this is summed up very nicely in figure 18.1, which clearly illustrates why we see the catalyzed reactions go more quickly. If you just focus in right here on the left-hand diagram, it should make perfect sense that this is a terribly endothermic step. It's definitely way uphill because look at this mess of an intermediate I have. I'm going from two neutral starting materials to a highly charged and oppositely charged intermediate. That's really energy uphill. In contrast, under either basic catalysis or acidic catalysis, I'm not changing the number of charges involved. In other words, in my starting materials under basic catalysis, I have a negatively charged starting material, and I have a negatively charged intermediate. So they're both basically the same energy. So it's a much smaller energy of activation that I need to get over to get this reaction to go. So figure 18.1 is a good one to understand. All right, so here's an example. I got a funky ketone and potassium cyanide and HCN. Looks like it's under aqueous conditions. Let's run through the mechanism. What's going on here? Well, if we cross out our spectator ion, we'll see that we have Cn-. But wait, we also have HCN. So, doesn't it make sense to protonate my ketone and make this intermediate? Well, no. It may look good on paper, but as is explained in some pretty good detail in the textbook, HCN is actually not a very strong acid at all. And so, I'm going to make this even longer. This is not a favorable protonation. There is only going to be this most minuscule smidgen of my protonated ketone present in the reaction mixture. So this actually is not considered under acidic conditions because HCN is not a strong acid. No, fact of the matter is, this is just a simple old basic catalyzed reaction to give me this particular intermediate, which now can happily and much more reasonably be protonated by water or HCN. They're actually not that far apart in pKa to give me my product. Alright, so think about the conditions and go back and maybe review pKa's so that you have a good sense of what a strong acid is and when it would actually protonate a carbonyl. Alright, well, we ended up chapter 17 by looking at conjugate versus direct addition, and so it's sensible to revisit that with our new set of nucleophiles. So in the case of the cyano group, Cn-, is that going to be a hard nucleophile or a soft nucleophile? Is it going to be direct addition or indirect or conjugate? Yeesh. It is C-. But the thing is, as we've just seen, it's kind of a middle of the road in terms. It's not a really strong acid, it's not a really weak acid. It's kind of in the middle of the road. What is the story here? Well, the story is that the Cn anion adds reversibly because it's not actually that difficult to kick this puppy back out again. And what we know from chapter 17 is that if this reaction proceeds reversibly, ultimately when my Cn- adds here instead, and I get this intermediate, that's a more stable intermediate. So because the cyano group adds reversibly, and we can go back and forth, attacking directly at the carbonyl carbon or in a conjugate fashion to give this guy, ultimately we see that well, basically, the cyanide group adds 1,4, or conjugate addition. So it's not as easily classified as a hard or a soft, but it's all boils down to the reversibility or irreversibility of addition anyway, and since it can be kicked out in a reversible addition step, ultimately we go via the conjugate route, as we learned in chapter 17. And so any of these soft nucleophiles, and something like methane thiol or an isoamine, they're all going to add 1,4 to give you the conjugate addition product. Alright, notice too that Carty gives you a nice example on page 895, but one thing he does that is not the coolest, and I actually just did the same thing, so let's go through this. I will definitely expect you to show me the rest of this mechanism. So this is going to give me this guy, and Cardi just shows a couple of arrows going to this guy. Well, let's not do that. Let's do the right thing and actually show the mechanism, which is to show that popping back down and picking up the proton to give me my product. So please don't ever write tautomerization in quotes on an exam. Show me the mechanism. Alright, so here is just a quick screenshot of some random reactions for you to play with. I will put the key for these in the next mini lecture, but it's basically just trying to keep you on top of things. Chapter 17. Boy, I can't even remember what chapter that's from. This chapter 18. Can't even remember what chapter that one's from. Chapter 17. What did I tell you? It's going to seem overwhelming, and you should think mechanism. A quick reminder that your choices are your nucleophile attacks here to make the enolate, your nucleophile attacks here to do direct addition, or that is keeping in mind that sometimes you may be under acidic conditions and protonation will take place first. Alright, that said, what's up next is the wild, wacky world of oxygen nucleophiles, but first, what do you call a deer with no eyes? I have no idea. Get it? No idea? No idea. Really bad. Really bad. Okay, see you in class.